Hi, all. Thanks for having me here. I'm going to be talking about some recent work on language processing in humans and how it's related to the universal properties of human languages. So the goal of this research program is to explain the universal properties of human languages in terms of what would be an optimal system for efficient communication among agents, crucially with fixed human-like information processing constraints. So the link here between this notion of communicative efficiency and the properties of languages is that we think that languages are going to be optimized so that the things that we want to, the messages we want to convey are relatively easy to produce and comprehend. I'm calling this the efficiency hypothesis. This has gone under many names and guises in the literature on functional linguistics. So using this efficiency hypothesis to explain things about languages entails two kinds of research. The first is that we want to develop theories about what makes utterances hard or easy to understand in terms of their information processing characteristics for humans. And crucially, we want to make theories like this that make predictions about languages. And the second thing we want to do is to test the predictions of those theories about languages, about the grammars of languages, and also crucially about the quantitative properties of usage. And the reason we want to look at both grammar and usage is that this notion of efficiency is grounded in the things that we actually say. This talk is going to focus on these two kinds of research applied to predicting word order universals about languages. So the basic the basic idea to have in mind is that we're defining something like a utility function for a language, where the languages we observe are going to be high utility, the languages we observe are the really rare, the languages that we don't observe are the really rare ones are going to be low utility. And utility is going to be something like reward minus cost, where reward is going to be something like information transmitted, and cost, which is the thing we're going to be focusing on in this talk, is going to be stuff like the processing cost for production and comprehension. This could also include stuff like grammatical complexity or learnability constraints could figure into this. Processing cost for language is going to be something like the expected processing cost for its utterances, which is just the average of the processing cost for each utterance. And this talk is going to be basically focusing on characterizing this cost function such that we can make predictions about languages. So the plan for today is first we're going to show corpus evidence for this concept of dependency locality, which is a classic idea coming out of the psycholinguistic and functional linguistic literature that for reasons of communicative efficiency, words that are in syntactic dependency should be close to each other. The second thing is we're going to present a new model of language processing difficulty called lossy context surprisal, which combines the effects of memory limitations and probabilistic expectations. And we're going to show that this model makes a new prediction, predicts a new principle for word order called information locality, which is a generalization of dependency locality. And finally, we're going to show that information locality can predict certain aspects of universals about the ordering of elements within noun phrases, which are not well predicted by dependency locality. So first, I'll be showing large-scale evidence for this notion of dependency locality. So in psycholinguistics, dependency locality is this concept that there's a preference in both online processing difficulty and in word ordering preferences for words in syntactic dependencies to be close to each other. And there's evidence for this from production preferences, from acceptability ratings, from online reading times, and controlled experiments. I'll demonstrate this to you with an example. So we can say something like, John threw out the trash. And I'm going to give this a thumbs up because this sentence is easy to understand. It sounds fluent and acceptable to native English speakers. We think the dependency exists between the word through and the word out. And I'm using the word syntactic dependency here in a very general sense. This is just a link you can draw between any syntactic head and anything modifying it. Another way to think about this is that these dependencies indicate places where there's context dependence in interpretation. So to understand what this word out means in context, you have to understand it as part of this larger unit, this phrasal verb threw out. So a dependency exists there. We could also say John threw the trash out, and then the dependency exists here, going over this intervening phrase, the trash. We can say something like John threw out the old trash when sitting in the kitchen. This sounds fine. I've just made the noun phrase there longer. But now this version of the sentence sounds a little bit weird and bad. So I can say John threw the old trash that's been sitting in the kitchen out. And as I make that noun phrase longer and longer, it's going to get worse and worse. I can say something like, John threw the old trash that's been sitting in the kitchen for months and months after the party he had with his coworkers out. And now it becomes almost incomprehensible. And we think part of why this sentence sounds weird and bad is that this long dependency exists between through and out. So if you imagine you're understanding this sentence, word by word, you're reading it or you're hearing it, by the time you get to this word out, in order to understand what it means in context, you're going to have to consider that it's part of this phrasal verb throughout. So that means that at this point, you're going to have to recall some detailed representation of this word that you encountered a long time ago. And the basic idea here is that this memory representation had to hang out in memory for a long time. So this memory retrieval operation you have to do here, it might be difficult, it might be inaccurate. And that could be because there's just inherent decay in your memory over time, or it could be because there's cumulative similarity-based interference, which is affecting your memory representation as you go through the intervening material. The point is just that there's, yes?
Don't the Germans do this all the time?
Yes. In some languages, so in a part of the talk that I'm not going to be covering today, but in other work we've discussed how different, so the size of the effect is going to be modulated in an interesting way by the language statistics of different languages, such that this kind of thing is going to be easier in German than it is in English. I'm not going to be covering that today, and that's part of the extended theory I'm going to be presenting that's not accounted for by just this dependency locality idea. So the basic idea for dependency locality is that this dependency length corresponds to the amount of time that a high fidelity representation of a word is required to hang out in memory. And when that when dependency length is long, then there's processing difficulty and there's potentially inefficient use of resources. So this idea has been used to explain a lot of disparate phenomena in psycholinguistics, including the fact that center-embedded sentences are hard to understand, and sentences with object-extracted relative clauses are harder to understand than sentences with subject-extracted relative clauses. So here's an example. This sentence, this is the malt that the rat that the cat killed ate. This is almost incomprehensible, especially to non-linguistic audiences. But it's actually synonymous with this sentence. This is the malt that was eaten by the rat that was killed by the cat, which is totally comprehensible. We think part of what's going on here is that if you look at the dependency structure for this, oh, I meant to do a laser, but I don't know what just, okay. Long dependencies in this multiply center-embedded sentences, shorter ones in this one. So now from this perspective about predicting things about languages and word order universals, the basic prediction we get out of this dependency locality idea is just that if languages are efficient, they should minimize dependency length. So words in syntactic dependencies should be close to each other in linear order. And in particular, both grammar and usage should conspire to make this so. So this idea is mostly associated, I think, with Jack Hawkins' work in typology, and it's also, there's been a huge amount of work that's done in this sort of paradigm from different researchers. So what I'm going to do now is I'm going to review three major aspects of natural language word order that people have tried to explain using this dependency locality concept. The first is that in languages that are primarily head initial, like English, you're going to have an ordering preference to have short constituents before long constituents. And here's why. So if you are in a language where the modifiers typically go after the thing that they're modifying, like English, if you put short constituents before long ones, you get short dependencies. If you were to do the opposite and put long things before short things, you'd get longer dependencies. So dependency locality says we don't want this, we do want this in head initial languages. But in head final languages, like Japanese, you would actually prefer to have the long things before the short things, the exact reverse, and there's some evidence that that's the case in Japanese word order preferences from experiments. The second thing we can predict using dependency locality, the second thing that people have tried to explain with dependency locality is this idea, is the fact that head direction is typically consistent within languages. So it's often the case that a language always consistently has modifiers after heads or modifiers before heads. And the reason that would be the case, the reason that would satisfy dependency locality is that if you have consistency in head direction, you get orders like this with lots of short dependencies. I'm just saying these are length 1. If you were to have inconsistency in head direction, you would end up getting long dependencies like this. So for certain tree structures, dependency locality predicts you don't want this kind of structure, but you do want this kind of structure. And this gives you the harmonic word order correlations, which have been highly studied in typology. They were initially discovered by Joseph Greenberg. And it also, for different tree topologies, you would actually expect inconsistency in head direction with satisfied dependency locality. And Gilday and Temperley point out that those correspond to some of the most prominent exceptions to this consistency in head direction across languages. Final thing that dependency locality can explain is that natural language syntax has this property called projectivity, which is that when you draw the dependency lines above words, like I was doing here, those dependency lines don't cross.
Well, when they do, there's plenty of language where they do.
They do, but it's rare. It's rarer than you'd expect from random trees.
Okay.
And
These are all about, like, just, you know, sort of pressures towards.
yes.
Okay.
And
They
also,
want to regain themselves. Okay.
and also the minimal dependency length linearization for a tree will not necessarily have projectivity, but it usually does. So just to back up, though, for people that don't know projectivity, so this might seem like, when I say the lines aren't crossing, this might seem like some kind of arcane graph theory thing, like who cares, right? But projectivity actually corresponds to something which is near and dear to linguists, which is context freeness, in the sense that a language which has only projective trees can be generated by a context-free grammar. So if dependency locality can explain projectivity, it might go some of the way to explain the actual formal class of natural language syntax. So here's an example of a non-projective sentence from Latin poetry. This is from Ovid. The word-for-word translation here is in, new, bring, soul, change, tell, form, body. And so the dependencies are just crazy. And you can see that when you have these crossing dependencies, which exist here probably because Ovid's trying to satisfy the hexameter and is maybe less concerned with efficient processing on the part of his listeners, when you have these crossing dependencies, on average, you're going to get much longer dependency lengths. Here's a projective linearization of the same tree. It has shorter dependencies. So dependency locality says we don't like this stuff, we prefer this stuff. So those are three things that we could use dependency locality to explain, and it's very cool that you can explain all this stuff from this very simple and easy to state principle. This very simple principle that things in dependencies should be short. The issue is, okay, so are dependencies actually short compared to reasonable baselines? And this is especially a problem because all those things I showed you have reasonable, independently motivated explanations. There's alternative explanations for all of these things. So this projectivity constraint could be motivated by this idea that there needs to be a certain kind of isomorphism between the semantic structure of a sentence and its syntactic structure. This consistency in head direction could be alternatively motivated by the idea that there's a simplicity bias in grammars. If you have a grammar that has consistent head direction, then you only need to learn one head direction parameter, and so the language is simpler and easier to learn. So now the question is dependency length actually minimized? Does dependency locality hold beyond what we'd expect from independently motivated constraints on languages? And so what we're going to do now is to test this claim. We're going to test this question in dependency tree banks. So I'm going to do a little detour here to talk about the data sources. So I'm going to be using cross-linguistic dependency tree banks from the Universal Dependencies project. How many people here are familiar with Universal Dependencies? It's usually like half the room. Okay. So this is a very ambitious project where the idea is to create large human annotated tree banks of text in many languages, all annotated according to the same syntactic dependency formalism. So here's an example of the kind of data you get from universal dependencies. So you get a large set of sentences for a bunch of languages, all annotated with this kind of structure. You get words, you get the parts of speech tags for those words, you get dependency arcs from head to dependent. So I is the subject of RAND, so we say there's a dependency there, and you get labels on the dependency arcs for basically the grammatical function. The data sources are mostly things like newspapers. There's things like blog posts. It's mostly written language. There's some spoken language, but it's relatively rare. There's also some ancient and liturgical languages in here, in which case the content is mostly religious. So if you look at this dependency tree, if you are a syntactician, you might notice this is kind of weird. So this tree is parsed such that in this part on the internet, this word internet, the noun, is considered to be the head of the on. So the idea here is that on is modifying the word internet. And this is unusual. So usually in syntax, we'd say this is a prepositional phrase, and internet is modifying on. It's not the other way around. So the reason universal dependencies does this way is so that they can annotate all languages consistently. But for the purposes of our study, we don't really want these kinds of dependencies. We want dependencies that are real syntactic dependencies. And so it turns out that in many cases, about 90% of trees across these corpora, you can automatically convert these things from their universal dependencies annotation to a more syntactically standard annotation where now the preposition is the head of the noun and you have a real prepositional phrase. And I've made the software for doing this transformation and for replicating all these results available online here. Here are the languages that I'm going to be presenting results for from universal dependencies. So you can see we mostly have Indo-European languages. That's because the universal dependencies parses languages that you can make money by parsing. And so it's not, we're not getting like languages from Papua New Guinea in here, not yet, but there's work on these things. There's still plenty of interesting languages here, like there's a variety of Turkic languages and East Asian languages. So this is, I think, the best typological sample you could currently get if you're doing a study of cross-linguistic quantitative syntax. So now here's how we're going to use the dependency tree banks to test this idea of dependency locality, of dependency length minimization. So we start with a real sentence from the corpus. So here's a real sentence. This story comes from the AP. And we can annotate its dependency length. We can measure its dependency length by adding up the length of all of the dependencies in the sentence. And so we're measuring dependency length here as just the distance in words from head to dependent. There's a lot of discussion in the literature on what the right distance metric is here, but they're all highly correlated, and this is something which is simple to do, and it's good enough, and the field seems to have converged around this for these kinds of studies. So the total dependency length, which you can see as a sort of measure of the efficient processability of this sentence, is we measure to be 6. Yeah?
Is there a reason you would do total rather than some sort of average? Or like in terms of minimizing like average dependency length? Is kind of the thing that was intuitive when we were talking about it before.
Yeah. So what are you thinking of taking the average over?
I mean, maybe it's like total number by total number of dependencies and then the total count, right? So the length.
Right.
The number that you have.
Yeah. So the results I'm showing could be, yeah, they could be translated into that kind of thing.
Okay.
Yeah. There's reasons that I'm not going to be doing that, but I don't know if I want to go into them. It's like, yeah. So what we do is, so we've got this sentence. We measure that to have dependency length 6, and it also has 6 words. So we're going to say this is sentence length 6. So we can plot this in a space. We can say, okay, this is dependency length 6, sentence length 6, so we're going to put this point here. And now we can plot the average dependency length per sentence length for all these sentences in the language, in the corpus rather. This is the observed dependency length per sentence length. And so this is a sort of dependency length growth rate, which is a sort of characteristic of the language which is determined by its grammar and its usage properties. So now we want to compare this to some kind of baseline. We want to say dependency length is minimized compared to what? So here's an example of a random baseline. One of the random baselines we look at is a projective random baseline. And what this says is, imagine that the only constraint operating on natural language word order is this projectivity thing that lines shouldn't cross. And then we can take, so what we do is we take that original sentence and we reorder it many times while respecting this constraint of projectivity. And this tells us what would this particular sentence look like if the only constraint on word order that anyone cared about was projectivity. And we can measure the dependency length in these random reorderings, and we can plot them into the same space. And then we can plot the average dependency length per sentence length if all that mattered were projectivity. And this is real data, and we see that it is, if projectivity were the only thing we cared about, we'd have longer dependency length than what we actually get in the corpus. And now we can do this for lots of other random baselines, instantiating other possible constraints on natural language word order, other possible independent constraints. And here's results from 6 different random baselines. These baselines represent things like consistency in head direction, if that were an independent constraint. And they represent, so these two, the red and the green lines that you actually can't see because they're underneath the other ones, represent what word order would look like if you had fixed order with respect to grammatical functions, but where that fixed order is random, it's a random grammar per language. And so what we see is that in English, dependency length is shorter than we'd expect from all these independently motivated constraints. And now we can generalize this to 54 languages from universal dependencies, and we see the same pattern. So in all languages, it turns out that the dependency length for observed sentences is significantly lower, the growth rate significantly slower, than you'd expect from any of the random baselines. And there's a lot of variation in the extent to which that's true. So if you look at Turkish, for example, It's not highly minimized compared to the random baselines. There's still a significant difference here in all the languages, but there's a lot of this variance. It's still the case that all languages show this dependency locality thing. So
is that connected to case?
there's a lot of interesting connections there. So I think part of the reason you see a difference between something like English and something like Turkish has to do with how the languages are segmented. So a language with a lot of case marking, you're going to have like a content morpheme and then a bunch of case markers on it, and that's just considered one word in the dependency tree bank. And so all those short dependencies that exist between the content morpheme and the case markers don't end up going into the calculation. And
versions of
yeah.
locality that do some of this morphological analysis?
Not in a consistent way, or not in a way that's consistent enough that I want to do it. I did do the analysis, though. I did this analysis removing all function words, which has the effect of, to some extent, neutralizing this difference in annotation across languages. And you still get the significance dependency locality effect across languages. It eliminates some of the variance across languages, but not all of it. Yeah, Mike?
So I know there are computational challenges,
Uh-huh.
and there are different ones depending on how you do it, but
Yeah.
you could imagine trying to actually minimize dependency length and look at those baselines.
Yes.
Either literally sentence by sentence minimize,
Yes.
or you could try to compute a consistent grammar that
Right.
minimizes what
So-
happens.
So that's what Gildea and Tepperley have done, and I used to present this plot with the extra lines for the minimal baselines. So what happens is that no language is completely at the minimal baseline. So you can imagine that. So basically, a language like English comes out very close to the minimal baseline, and a language like Turkish is very far from it. So if you sort of imagine transposing something like the English observed curve down into Turkish, it's going to look something like this. So there's variance in how closely we approach the minimal baselines.
That variance seems like that would be a kind of an object of typological analysis.
Yes, so I think it's an open question why there's this variance across languages. I think it's extremely interesting, and it's the sort of next frontier, one of the next frontiers for this kind of study. Yeah, Tim?
To what degree so one would assume, I guess, that sort of the Calderian mobiles that
Uh-huh.
underlie these trees are roughly identical across
Mhm.
linguistically. Is that true?
The languages, well, they differ quite a bit in things like their arity, and that's because of this function word question, I think, mostly.
I see.
You could imagine doing things the other way and saying, fixing the word order rules, look at the tree structures, and maybe those are also optimized. I haven't done that. That's harder because it's hard to define what it means to fix the word order rules. But it's easy to define what it means to fix the tree.
It seems like, to the degree that we believe that the sort of underlying compositional structure is roughly the same cross-linguistically,
Mhm.
that seems like an important thing to control for. Or maybe we don't believe that, in which case it's an important thing to study.
So, I mean, one way to see this is that we've, within each language, controlled for its particular tree structures and found that the word order rules, rather than the tree structures, have this effect of minimizing dependency length. Yeah, Bernard.
A lot of languages, that straight line at the end,
Uh-huh.
sort of squiggles.
Oh,
A
so,
lot of languages
yeah.
do that.
Oh, well, we start to run out of data at the long sentence length. So this is like sentence length 50. These are very long sentences, and there's not a lot of them in each corpus. And so the mean starts, the variance, there's less data out there.
Is there any way to control, like, following up on what Tim was saying, any way to sort of control for arity?
Mhm.
Like, so you imagine if something it has arity of, a verb has
Mhm.
arity of 5 or something,
Mhm.
it's a high number by any account, that you might
Mhm.
imagine that, like under sort of a distributed morphology view
Mhm.
of the world, that means that there's actually a lot of stuff inside of that token,
Mhm.
right? Is there any way to sort of control for that you've come up with?
So I don't know what
Is
we,
that- is
yeah.
that correct? Is that analysis correct, for instance?
So I don't know what we would need to control for in particular. So the tree structure is controlled within each language here.
Mhm.
And this is just saying that whatever the tree structure is, the word order rules give you dependency locality.
I can just imagine that like arity would make it harder to have a short sort of high
Yes.
arities make it harder.
Yeah,
right?
exactly. Exactly. So you get the lowest dependency length if you have arity 1 for every head. Then your dependency length is sentence length minus 1 or something. So
That has to do with,
yeah.
just has to do with the quality of the minimal and random baselines and top lines, I guess, too.
So people have looked at comparing to actually just straight up random trees in it, rather than just random reorderings of the observed trees, and you find the same effect. You find a stronger effect, in fact, when you compare to that baseline. And it makes a lot of the cross-linguistic differences go away. So a lot of what's driving these differences might be these tree structure stuff. So dependency localities is pressure for words and syntactic dependency is to be close. Motivated by this notion of processing efficiency, sentences we think are going to be high cost when they have long dependencies. We show that it can explain these three major properties of natural language word order, and that it's minimized beyond what we'd expect from independently motivated baselines. So now what I'm going to be doing is I'm going to be digging deeper into the processing model that underlies this notion of dependency locality. So I've been talking about this idea of processing difficulty that's basically a result of limitations on the working memory you're applying when you're processing a sentence. But it turns out there's a large class of sentence processing difficulty phenomena that are not explained by any kind of memory-based model. And these are basically effects of probabilistic expectations. I'm going to demonstrate this to you with a sentence. So I'm going to show a sentence to you word by word very slowly in order to simulate to you what it's like to hear this sentence or to read this sentence word by word. So imagine you hear thee, then you hear troops, then you hear attacked, then you get this word by. And this word by is probably very surprising at this point. And then the rest of the sentence is the troops attacked by the enemy suffered heavy losses. So we observe reading time slowdown and a lot of processing difficulty at this word by. And the reason appears to be that after you hear something like the troops attacked, usually expecting that the troops are attacking something, and then you're expecting to find out what they're attacking. You're not expecting them so much to be attacked by something, as in this reduced relative. And so you can get this word by. Essentially, it's not what you expected, and so you get difficulty integrating this word into your representation of the sentence. So this notion of processing difficulty, that's the result of this notion of surprise, has been formalized in the theory of surprisal theory. And what surprisal theory states is formally that the processing cost for a word given a context is going to be proportional actually to the negative log probability of the word given the context. So why are we taking a negative log probability? The reason is basically that the negative log probability gives you a function that looks like this. So if you imagine that on the x-axis here we have the probability of a word in a context, so this is a high probability word, this is a low probability word. The y-axis tells you the negative log probability, which is what we call the surprisal. So a really predictable word is not very surprising, and you're not going to have to do much work to integrate it into your representation of the sentence because you already expected it. A really low probability word is very surprising. You're going to have to do a lot of work. Surprisal can also be thought of as a measure of information content. So if something is very predictable, it doesn't convey much information because you already had the information. So let's think about how we would apply surprisal theory to describe the processing, to predict the processing difficulty for a sentence like this. Here's the picture to have in mind. We're going to be looking at the predictability of a word given a context. So the difficulty for the word thee is going to be the negative log probability of the word thee given the context of the beginning of the sentence. And then difficulty for the word troops is going to be related to the probability of troops given thee. Then we'd look at the probability of attacked given the troops. Then we'd look at the probability of by given the troops attacked. It's going to be low probability, high surprisal. There's your processing difficulty. And you go on processing the whole sentence in this way. And here's the actual surprisal profile for this sentence. And you can see it spikes at by.
So how do you measure the probability?
So this is from a smooth trigram model. But in principle, so a smooth trigram model is, it's basically a tool from computational linguistics for getting the approximate probability of a word given its context. So there's,
Given a bunch
yeah.
of sentences?
Yes, given a bunch of sentences. So in principle, what the theory is describing is, for you, what's your subjective probability of what's coming next, given all the context you're bringing to bear on that question.
So it could be both
Yeah.
like the syntactic predictability
Yeah.
and the semantic predictability.
All that
So
stuff.
how else is going on
Yeah.
is supposed to be, and so the trigram is an approximate
Yeah.
heuristic for that.
Yeah. So in practice, we can't measure the actual predictability of what we're given a context. We have to approximate it with things like trigram models, or you can use probabilistic grammars or all kinds of things. So that's the surprisal profile. So now we're basically left with two kinds of theories of language processing difficulty that I've described. There's theories like surprisal that are based on probabilistic expectations, and there's theories like dependency locality that are based on these memory limitations. These are two very different things. They make, in many cases, complementary predictions. They explain complementary sets of data, and there's also some interesting interactions. it's proven challenging to combine these things in a satisfying way in a unified theory. Typically, these things are combined together. If you want to predict reading time, you just combine these two things together as two factors in a linear model, essentially. So what I'm going to talk about now is what's the right way to make a model of processing costs that combines surprisal with memory constraints. What does that mean for this notion of dependency locality that we've been talking about? So the theory I'm going to be presenting is called lossy context surprisal. Here's just a reminder. Surprisal theory says processing cost for a word in a context is the negative log probability of the word given the context. So now let's think about how we would model the processing difficulty at the word out, given a context like Bob threw the old trash bin sitting in the kitchen. So no surprisal theory, as I've described it, is going to capture the difficulty at this word out, because these theories are all based on perfect knowledge of context. And given perfect knowledge of context, the only thing that grammatically you're going to have to get a word out or something like it later in this sentence. So here's the sort of model that underlies surprisal theory. You have a context, and that context constrains the next word that can follow. In some sense, we can say the context causes the next word that can follow. And where the context is the true context, the thing that the speaker actually said. So you're taking the context and you're predicting the next word. But this really isn't quite right. So if you don't actually have access as a comprehender, or really as a producer, to the true context that generated the word. Rather, you only have access to your memory of what the context was. So the past is a foreign country. We're sort of seeing through a glass darkly when it comes to memory. So here's a more realistic picture. There's an objective context which causes the next word. You don't know what that is. What you have is your subjective context, which is what you remember from the objective context. And you're using your subjective context to predict the next word. So now the question is, what is this link? How can we think, what's the link between the objective and the subjective? That's a hard question, right? I'm going to say that a simple way to think about this is just that the thing to focus on is that information loss happens when you're going this way. So your subjective context contains, in some sense, less information than the objective context. And we can model that by saying your subjective context is just your objective context with noise added. So you imagine your subjective context is this noisy thing where you can kind of make out what the real context was, and you're using that to predict what's coming next. This is the basic picture for lossy context surprisal. And here's the math. Processing cost for a word given its true objective context, which you see as an experimenter, is its negative log probability of the word given the subjective context here. And we're going to take an expectation, we're going to take an average over the possible subjective context given the objective context according to some model, which we call the noise model, of how the objective is transformed into the subjective. So this is just going to be a model that models how information is lost as you go from the objective to the subjective here. So now let's think about applying this model to this case of Bob threw the old trash.
Wait, are you going to tell us about the noise model?
Yes.
Awesome.
So yeah, right. So essentially, this is a major free parameter in this model,
Yeah.
but it's constrained in that it does a lot of work. It's constrained in certain ways.
Mm-hmm.
So for example, you couldn't have a noise model that actually you couldn't have a model where a context representation gets, in some sense, better over time, right?
If only by chance, I suppose you could,
Yeah.
but it's unlikely.
We can talk about it. It's actually there's bounds you can put on this, such
I
that
wasn't
yeah.
around, I just was very curious.
No, this is really, I think in applying this model in the future, varying this noise model is going to be how we get it to explain all kinds of stuff. So in this example though, Tim.
Could I ask why the expectation is outside of the log?
Right, so this is, there's a subtle point here, and I think actually for modeling the producer and the comprehender, it might be different. For what I'm presenting here is just the model for the comprehender, in which case your difficulty has to do with the actual subjective context that you happen to have. And so, like you as a comprehender, you're not thinking, okay, what are all the subjective contexts I might have?
So we're lifting the analysis essentially, so that we're doing analysis over like hypothetical idealized comprehenders.
Yes.
Right?
So and that
each
yeah.
idealized comprehender has a log probability base, a survival base.
Yeah.
Okay, got it.
And so another subtlety there is that that expectation, that average, that you can see that as I think the simplest way to see that is an average over different participants in an experiment, say, or over different people. It's not clear that it has to be that way, but that's something we can discuss offline.
And
Yes?
also it doesn't have to be the log. It can be just any function that looks like this, right?
So there's quite deep reasons that it has to be the log that I don't want to, like, I could talk about that for like 30 minutes. So basically the logarithm is sort of the right way to translate statements about probability into statements about information. And in some sense, so what the logarithm, you can see the way you can interpret the logarithm is it's telling you, in order to arrive at a certain interpretation, how many binary cuts do you have to make? How many binary decisions do you have to make starting from your prior beliefs to get to the posterior beliefs? And that provides a sort of hard conceptual lower bound on how much work you have to do in order to update a belief. I don't know if that was comprehensible. We can talk about that offline, but there's a whole universe here in explaining why that's the logarithm in particular. So we're trying to predict out, given Bob said the old trashman sitting in the kitchen. We think the key word for predicting this word out, the word that really mattered, was this word through. Now let's suppose that this noise rate that's affecting our context representation is increasing the farther back, the extent to which it affects word representation increases the farther back those words are in memory. So your lossy context looks something like this. This is just expressing the intuition that we remember the sort of gist of a context, but we rapidly lose specific information about things like word forms as we go back. If we have a noise model like this, then when we have a word like through that's far away from a word like out, then the word through is not likely to be available in your context representation for predicting the following word out, in which case the word out is going to be surprising. On the other hand, if the word through is close to out, it's less likely to be affected by this noise, more likely to be available to predict the word out and make it less surprising in context. And this is, the basic prediction here is lossy context surprise is going to increase when words that predict each other are far from each other. This is information locality. So I've shown the basic idea for information locality here in an example. Now I'm going to provide a more detailed derivation of it from the processing cost model in order to give some intuition about what's really going on. So in order to do a concrete derivation, we're going to have to make some concrete assumptions about the noise model. How do we model the lossiness of memory representations? And so what we're going to do here is something which is modeling just the gross properties of forgetting in a way that is mathematically convenient. So what we're going to say is that a word is going to be probabilistically marked as erased with some probability that increases the farther back it is in a context. So let's say we're trying to predict the target word out given the contexts Bob threw the trash. We're going to consider noisy subjective contexts like this one where the word through got erased. Or we'd consider ones where maybe trash got erased, consider ones where maybe multiple words got erased, and where the probability of erasure is increasing monotonically as we go back. And I don't want to say that this is what memory is actually like. You're probably not just probabilistically erasing words. What this is modeling is just the gross fact that you're losing information about word forms at an increasing rate as you go back.
So when you lose, like let's say you erase some words, like the subjective context you just had up there, then is the remaining, do you just do sort of your smooth trigram prediction based on the remaining words? Or like how do you,
Right. So,
what do you do with your
so if you have a subjective context and you're predicting the next word, what you have to do is you have to marginalize over the possible objective context that could have given rise to the subjective one. And it's a sort of noisy channel model. So your memory is basically a noisy channel that you're using to predict. So right.
Got it.
Okay. So here we go. So under this idea, under this noise model where you have an increasing rate of erasure, it turns out you can approximate the lossy context surprisal function in the following way. You can say the processing cost for a word in a context is going to be approximately equal to the negative log probability of the word without context. This is just its unigram surprisal, minus the sum of the extent to which each context word predicts the target word, weighted by the probability that that context word was not erased. And that's somewhat dense. So first I want to point out this PMI thing here. This represents the extent to which a context word predicts the current target word. So pointwise mutual information is the most general statistical measure of the strength of covariance between two values. the extent to which two things predict each other, the extent to which two things constrain each other's values. So here's how we would unpack this for this example. We're trying to predict the processing difficulty for the word out given Bob threw the trash. To do that, we start with the log probability of out without considering context. This is the information content of out without considering any context. Then we subtract the extent to which out was predicted by Bob, which is probably not much, weighted by the probability that Bob was not erased by that noise model. Then we subtract the extent to which out was predicted by through, which is probably a lot, weighted by the probability that through was not erased, and so on for the other words in the context. Now there's two things to note. The first thing is I've said that the surprisal reduction that's due to each word is not, there's no overlap between these things, and that's why this is an approximation. But the error introduced by this approximation is bounded. The second thing to note is we think most of the surprisal reduction at the word out is coming from the word through. So this is sort of the key word. So just for illustration, I'm going to pretend that through is the only word for predicting out and the other effects are negligible. And now let's think, under these circumstances, what's going to happen as the word through gets far away from the word out. So as the word through gets far away from out, probability that it's not erased decreases, and so its effective surprisal reducing effect also decreases. And so the effective processing difficulty for the word out in this context is going to be larger. So when context items are far from the things they predict, you get more, their cost reducing influence on those things decreases. And that's information locality. Information locality is I predict processing difficulty when words that predict each other in the sense that they have high mutual information are far from each other. I've been saying that this is going to have something to do with dependency locality, which I spent some time talking about. They're actually logically unrelated, but these things are connected under the following linking hypothesis, which is that words in syntactic dependencies also happen to be those word pairs that have high mutual information. They have higher mutual information than all the other word pairs. And there's reason to think this is true. So there's a priori reason to think this is true. So mutual information, remember, is this measure of the strength of covariance, the extent to which two variables constrain each other. And syntactic dependencies seem like they identify word pairs whose covariance is constrained by grammar. So there's some reason to think that mutual information and syntactic dependency might be deeply related. So if it's true that the words in dependencies are also the words with the highest mutual information, then we can see dependency locality effects from before as a subset of information locality effects. So we can see dependency locality as a sort of first order approximation to information locality that you can do by annotating trees rather than by calculating mutual information from billions of tokens. So what I'm going to do now is show that this linking hypothesis is true in the dependency corpora. So what I'm going to show here is for the dependency corpora, I'm going to show the measured mutual information between part of speech tag pairs, and I'll talk in a bit about why we're doing that rather than quantifying over word forms. For words in direct dependencies in red, this is what we predict to have the highest mutual information. For words in indirect dependencies in blue, this is words where you have one word which is the head of some irrelevant thing, which is in turn the head of the second word we're looking at. And we're going to look at words that are in a sibling relationship, words that are mutually dependents of the same head. And we're going to quantify mutual information over part of speech rather than over word forms for reasons of data sparsity. So to get reliable estimates of mutual information, this is a famous estimation problem in information theory. You need many, many, many tokens, many more than we have in the universal dependencies corpora. By looking at parts of speech, we can get more stable, reliable estimates of mutual information, at least a subset of it. So what we find is that in all languages with great consistency and with statistical significance across all of them, in all languages the highest mutual information is concentrated in the direct dependencies, and these other relationships have less. So I predicted, yeah, Mike?
Sounds like you've thought about this. I'm just curious. So MI has this kind of well-known frequency-related confound, and those dependency structures seem like they might suffer from sparsity
Yes.
constraints that would be correlated with that.
Interesting. So especially the sibling thing is going to be affected by that less than the indirect dependencies. It's not. So the interesting thing about the MI bias is that so entropy is biased. So when you measure entropy from a finite sample, it's always lower than the true entropy on average. It's on average lower than the true entropy. With mutual information, you don't know if the number you get is too high or too low, because it's like mutual information is one entropy minus another, right? So it actually goes up and then down. And so we sort of don't know where we are on that curve with these plots. But we assessed the convergence. So these, for the parts of speech tags, the mutual information values have converged for these. We did this in August in 2016. So information locality is that we predict processing difficulty when words that predict each other are far apart from each other. If words in dependencies are also those with the highest mutual information, that means we can see dependency locality as a special case of information locality. But information locality makes a much more general prediction, especially about word order, which is that when we look at the mutual information of words at various distances, we should expect that words with the highest mutual information are close to each other. And this should be true this should be true for all words, and it should also be true for words that are in syntactic dependencies. So as an effect beyond dependency locality, those words in dependencies with the highest mutual information should be close to each other. So what I'm showing here is the measured mutual information, again, between part of speech tag pairs for words at various distances. So this is the mutual information between, in blue, for all words at distance 1, which means these are directly adjacent words, out to distance 5. So these are words where there's 4 things intervening. In blue, I'm showing the mutual information for all word pairs. In red, I'm showing the mutual information for the subset of words that are in a syntactic dependency relationship. And what we see is that with great consistency, mutual information falls off with distance across languages. And this is an effect beyond dependency locality, because this also holds for words that are in syntactic dependencies. And what the stars here show, these indicate positions where the mutual information of words in direct dependencies is significantly higher than the mutual information for all word pairs. So this is just more evidence for this claim that words in dependencies are those words with the highest mutual information. So information locality predicts that words that predict each other should be close to each other. It's derived from a theory of processing difficulty that incorporates effects of probabilistic expectations and memory. In other work, we've shown that this model can account for structural forgetting, which is this interesting, almost paradoxical phenomenon where it looks like effects of memory are language dependent, but I don't have time to present that today. The main new prediction that's coming out of this for online processing and for word order preferences is that dependency locality effects should be modulated by PMI, pointwise mutual information. And the picture I'd like to push is that dependency locality, these classically studied things, are a subset of this larger class of things called information locality effects. So what I'm going to be doing now, are there any questions at this point?
Just as a note, maybe a couple of minutes, and then we have to wrap up.
Okay. Yeah. So I actually don't know if I can go through this in any appreciable detail in a couple minutes. But
Try.
okay. Here we go. Okay. 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 Cut me off. Cut me off brutally. So I'm going to be applying information locality to explain certain ordering constraints which are not well accounted for by dependency locality. And these are the constraints on the orderings of elements within noun phrases. So in a noun phrase, here are the four of the things you're likely to encounter. There could be a demonstrative, a numeral, an adjective, and a noun. So for example, in English, this would be corresponding to a noun phrase like these 3 red cars. And in English, these things have to occur in this order of demonstrative, numeral, adjective, noun. And so now what I'm going to show is the cross-linguistic distribution of orders for these 4 elements in noun phrases. So what this plot's going to show is for all the possible orderings of these 4 things, how many unrelated language genera have at least one exemplar language that has that order as the dominant order, according to a typological study. And so to orient you, this order here is the English order, demonstrative, numeral, adjective, noun. And here's the typological frequencies. So we see that the English order is actually the second most common frequency across, most common order across languages. The most common order is the reverse of English, which is noun, adjective, numeral, determiner. And there's also quite a bit of languages that have rarer orders. So there's a number of explanations that have been adduced to explain this frequency distribution over orders. One of the most prominent is this theory based in generative syntax from Cinque. in which there is a there's a particular hierarchical structure with a linear order associated, and which is the English order. And all the other orders are derived from that by various movement operations, which are marked to various degrees that give you this frequency distribution. There's also been more descriptive work that's focused on sort of breaking down this data into 4 or 5 features that can be modeled in a regression. There's also theories, again, that the major constraint for these things is that there should be a certain kind of isomorphism between the linear word order and the semantic structure of these sequences, in the sense of that the order in which words are combined to form meaning should correspond to linear order in a certain way. And we've done some work to evaluate the empirical adequacy of these different things. So if we want to try to explain the word order for these things using something like dependency locality, something like I've been talking about, we're immediately going to run into a roadblock, which is that the dependency structure for these things is not actually clear. So the most common analysis you'll see for these things, the kind of thing you would do after Ling 101 or Syntax 101, is what's called the NP hypothesis. This says that the correct dependency structure for these things has the noun as the head, and the demonstrative, the numeral, and the adjective jointly as modifiers of that head. The other common analysis for these things from the syntactic literature is the DP hypothesis, which stands for determiner phrase hypothesis. This is currently what's common in generative syntax. Under this analysis, you take the demonstrative to be the head of the adjective to be the head of the numeral, demonstrative head of the numeral to be head of the adjective to be the head of the noun. So these very different structures, and they're going to give very different predictions if we plug them into dependency locality and see what word orders they prefer. So under the DP hypothesis with dependency locality, you prefer these top 2 orders, which is great, but the theory also says that all the other orders are going to be equally bad, so that's not great. Under the NP hypothesis, you're actually going to prefer word orders where the noun is central to the phrase, like you get in many Romance languages. It actually predicts that all these orders should be equally good and all the other ones should be equally bad. So that's not great either. Now the question is, can we make predictions in this domain using information locality? In order to do that, we're going to need to consider the mutual information between various elements. So what I'm going to show now is mutual information between the noun and the adjective and the numeral and the determiner. This is data from Marieke Schellstra's work. So what this shows is that the calculated mutual information calculated over word forms in the Brown corpus between the adjective and the noun is higher than that between the numeral and the noun, and that's higher than that between the demonstrative and the noun. And there's reason to think that this is intuitive. So if you think about mutual information as this concept of strength of constraint or strength of covariance, and then think about the mutual information between a noun and a demonstrative. So a noun is telling you a referent, but demonstrative is a word like this or that or these or those. It's basically telling you something like how close the referent is to the speaker. And it seems to make logical sense that the referent you're talking about doesn't strongly constrain whether it's close to you or not. These seem like relatively independent things in the world, and so there's reason to expect there should be low mutual information between the demonstrative and the noun. Also, the demonstrative is a closed class of words. It's basically this, that, these, those. And so that puts a hard upper limit on how informative the demonstrative can be about the noun. So here's the same study done on childless. And we expect that the same pattern is going to, and we have some preliminary evidence that the same pattern is going to hold across languages. So I think you can see where this is going. Information locality says elements with high mutual information should be close. Let's operationalize that for this particular study in the following way. I'm going to say there's an information locality criterion. And so here's what this would mean. So suppose we're looking at the ordering of elements A, B, and C, and we want to decide whether we want the order A, B, and C or B, A, C. And further, suppose that the mutual information between B and C, represented with this thick line here, is greater than the mutual information between A and C. We're going to say a language violates the information locality criterion when it puts something with higher mutual information strictly farther out than something with lower mutual information. So we're going to like this, and we're going to disprefer this. Note that I'm assuming here that there's going to be negligible mutual information among A and B, or among things like determiners and numerals. And that's an assumption we'd like to roll back in the future to make quantitative predictions. So I'm going to color these bars for the different orders according to whether they follow information locality as I defined it there, and whether they don't. Red when they do, blue when they don't. And we see that information locality picks out the top most frequent orders. It's still, it also prefers some of these more rare orders, and there's a bit of frequent orders that it doesn't quite get. But it has the advantage over the NP hypothesis, DP hypothesis, dependency locality stuff of picking out the top things and doing so without having to commit to a particular syntactic analysis.
And is that, we're sort of reaching the time point, so.
Yeah, so we're not going to do adjective order.
Yeah, I'm just sad. 'cause I don't know.
But it's basically the same story.
Okay.
So you'll get a quick preview of.
And again, we can revisit some of this during
Yes.
the extended question session, but just want to
Okay.
make sure that we
All right,
I know, it's always exciting.
this is a preview.
I know. Keep this in mind, because something's happening during the question session.
So wrapping up, I showed large-scale evidence for dependency locality effects on natural language word order from corpora. I presented a unification of surprisal and memory-based theories of language processing difficulty, which derives this concept of information locality as a generalization of dependency locality. And I show that it can predict certain aspects of noun phrase internal word order and some aspects of adjective ordering. The overall picture I want to push is that memory constraints push against all forms of long-distance context dependence in language. So information locality in its most general sense means that context-dependent linguistic elements like words, morphemes, even phonemes maybe, should be close to the context they depend on. And the reason is very simple. Context dependence is bad if you don't remember the context, right? And I think this corresponds to this old idea that the fundamental principle of word order is things that belong together mentally should be close to each other. I think going forward, this can provide quantitative mathematical models for things like order asymmetries between arguments and adjuncts, could provide models for things like word order change, could explain why different levels of linguistic structure exhibit different degrees of contiguity, different degrees of tolerance to elements intervening, as part of a quantitative explanatory theory for functional linguistics. So, thanks all.